going to share my screen. I'm going to share my screen and then let me know when you see it. Can you see my shared screen? Yes or no?
Yes, sir.
Okay, all right, you can see it. All right. So today I have a 3 session to lecture. So it's going to be this is the topic of the next 3 sessions. So the first is going to be as I mentioned yesterday, it's going to be the problem-based learning activity. So how to estimate the large reactor size using laboratory data. Okay. So if you have a laboratory data, but you want to build the large reactor, how do you do the estimation on the reactor volume? Okay. So that's I will show you one simple example. Then I'm going to share the screen on the chemical looping. I asked Dr. Anand to send you the paper, and then I want the whole class spend maybe 20 minutes talk about it. It should be easy, and then you can talk, and then I will point to you which graph in the paper you need to do the calculation. Okay, so that's the first session today will be the problem-based learning. How do you estimate the different size reactor? Okay, so with the limited laboratory data. Okay, and then the second part of the second session, which is after the break, and going to be downstream low pressure ammonia separation. So remember, Haber-Bosch process is high pressure reaction, and then you have to use high pressure cryogenic. By using the new technology like a microwave, a plasma, or the chemical looping, we are able to operate at low pressure. Is that right? So to operate low pressure, you need a low pressure ammonia separation because you already reduced the reaction pressure. You don't have to go back to use the cryogenic high pressure condenser. So yeah, so that means we have to discuss about what are the low pressure ammonia separation. So that's what I'm going to talk about. Then the third part of my presentation today will be the techno-economic analysis of a plant modeling. So basically, we are looking at not only the reactor, we are looking at the downstream separation, feedstock pretreatment, the whole ammonia plant. What's the techno-economic analysis, different cases. Okay. So anyway, I will walk through today, but step by step, we need to talk about how to estimate the large reactor size using laboratory data. You only keep in mind you only have laboratory data, but you want to build a large reactor. What's the rule of thumb and how do you estimate and what data you need to measure? Okay, make sense? All right. So I'm going to show you some of the quick estimate. Then we can go from there. So let me show you the reactor first. Okay. I want to give you some quick background. Go back to I want to show you the reactor configuration like we lecture today, so it's easy where you get the data. Okay, so can you see my screen?
Yes, sir.
Okay.
Yes, sir. We can see.
So basically, this is a laboratory microwave reactor. It can be any reactor. It's continuous flow microwave reactor, and you have the online analyzer IPR. Online analyzer means you have hydrogen, nitrogen flowing through, and then you have the ammonia come out. You analyze that. Remember, we did a calculation. One of case study I show you. You know, with 100 cc per minute nitrogen flow rate, 300 cc hydrogen, and how you calculate conversion. All right. So after you calculate conversion, one data you need, I'm going to write it down. You need a data called specific activity, which means so there's a terminology called specific activity. So the specific activity that is defined as gram of ammonia volume per volume catalyst per hour. So let's say if you use analyzer, measure the flow rate, conversion, and then you know the volume of catalyst, all right? So then and then you already have flow rate. So then you obtain the number of the gram of ammonia per volume of catalyst per hour. So yeah, that's the basic setup. So typically you need to I can give you the number. Let's say for the ammonia synthesis, probably the best you can do is 0.6 gram ammonia per ml of catalyst per hour. So what does it mean? So in 1 hour, one volume of catalyst can produce 0.6 gram of ammonia. Make sense? Okay, so that's called specific activity. So based on this laboratory, you can get this number. Okay, so let's go back to the all the other slides. Okay, so keep in mind. Okay, so this is the data you have. So now the question is, so basically I want to build a reactor with a capacity of 1,000 kg per day. Just read my question, okay? I want to build a reactor with a capacity of 1,000 kg per day. So that means it's a large reactor, and then you want to build it, and then they produce 1,000 kg ammonia per day. So how big is the volume of the reactor? You follow me? If somebody has any questions?
The thing is how much hours it's out of 24 hours or 8 hours or how much hours?
I could not hear you. Can you speak very slowly because your microphone has some feedback. I cannot hear you. So speak very slowly. Ask you what's the question?
Yes, sir. The question is, you have mentioned the hours. So hours means 24 hours or working hours like 8 hours.
Thank you. Okay. So all right. So how basically now we need to calculate how big is the volume of reactor. All right. Now you calculate. Okay. So very good. Okay, so let's so per day, that's capacity. Okay, so start calculation. So with this data, so for simplicity, let's change this. Okay, and 1.0. Okay, so lab data. So for in 1 hour, 1 ml of catalyst, you can produce the 1 gram ammonia. So as someone just said, in 24 hours, you will produce 24 grams per mil, 24 hours, or maybe it means per day. Make sense?
Yes.
All right. Okay. So now you get answers. All right. So that's why what's important is the laboratory data. Laboratory data you have to get it correctly. Okay. So that's a lot of measurement. But a large reactor, this 1,000 kg per day, you haven't built it yet. So but you want to estimate, hey, how much catalyst I need to buy. So this is how you use the laboratory data. So 24 gram ammonia per mil alpha per day. Okay. So that means if you want to build what you call that 24 gram ammonia, you want to build 1,000. So this is going to be how much? So this is going to be 1,000 kg divided by 0.024 kg. All right. You follow me? So this is equals need to move up a little bit. All right. So basically the answer will be 1,000 divided by the 0.024. That gives you the volume of the ml. Is that right? Volume. Make sense? So I'm going to calculate. Okay. Now. So it's divided. So the answer is you need 41666 mil of catalyst, which is about 41.7 liter of catalyst. That's the answer. Okay. So the answer is you need to buy this much of the catalyst. You times the density of the catalyst. That's the weight. Okay. So, but I want to show you the volume. Oh, to say different way, your reactor volume should be 41.7 liter. Make sense? Do you guys understand what my calculation?
Yes, sir. Yes, sir. Yes, sir.
So the key is you need to, in the laboratory, you need to measure this data. That's the key. Okay. This is the key. You need to get this piece of data, which means in 1 hour or in 1 day, whatever you name, per unit time, per unit volume, what's the productivity for the ammonia. So that's laboratory data. Based on this data, you can roughly estimate. But I can tell in reality, it's not linear, which means it's not from the small reactor. You can linearly do that. But this is roughly rule of thumb. This is correct. You need 41.7 liter of catalyst. Okay, it's pretty simple, all right? Keep in mind, you are looking for this data. Okay, is it clear now?
Yes, sir.
Okay, now is it clear? Let's go by paper. I want to give you 10 minutes. Okay, I'm going to show you the paper. I hope you read it. If you don't read it, for students who haven't read it, it's fine. Just remember this example. You are looking for this yellow highlighted data from the paper. You can read it. Okay, so let's go to the paper. All right, I'm going to stop sharing. Let's go to the paper I sent to you 2 days ago. I think Dr. Anand said you guys receive it. You received 3 papers, 2 we lectured yesterday already. One is the microwave chemical looping. The other is the microwave plasma chemical looping. That's from my group. The first one is from the Dr. Peter Fromm's group, and then he calculated how much the material needed. So I'm going to share with you. Let me go back and find the paper. Paper. So the example I give you, I oversimplify it. Okay. So this is a real world example. Can you see the paper I shared on the screen? Okay. So this paper by this gentleman whose name is Peter Fromm. Actually, I know him very well. So he did the chemical looping using the conventional heating. So if you read or you haven't read this paper, it's okay. And then I want to show you what I need from you. Remember this diagram? I show you the chemical looping. The using manganese catalyst, nitrogen has to dissociate so in the bulk. And then we lectured this already. I don't want to repeat it. But remember, he did 3 cycles. In the summer, I think I highlighted. I think when you receive paper, you see my highlighting. Okay. I want you to read this. Where is the highlighting, please? Okay, here we go. It's called the scale up estimate. Example I show you is a scale up estimate. You have a laboratory reactor, which is only the 1 mil catalyst. You want to scale up, you have a laboratory reactor only produce 1 gram catalyst ammonia per hour. You want to scale up to produce 1,000 kg. So that's called scale up analysis. So I want everyone spend maybe the 2 minutes, read this conclusion if you haven't read it. But if you read it already, I'm sorry, I apologize. If you read it again. I'm targeting the student who has not read this paper, read this paragraph, please. Okay. Yeah, read it. I will show you my example. Then you can spend 10 to 20 minutes and do the homework, do the calculation. So everyone finish reading? You finish? Everyone read it, all right? It's very, very complex, okay? I'm going to interpret this to you. So basically, in laboratory, he assumed a yield of 2.2 millimole ammonia per 5 grams of manganese. But the problem is, you see, he did not give the time. How long it took to produce 2.2 more ammonia with 5 grams? Okay, so what's missing is the time. how fast. I think that there's a lot of missing link here, but just keep on reading. An improved average the magnetic particles 2 micrometer, this data. So he basically spent the whole thing, the paragraph here. Did you hear somewhere he also using a shrinking core model? Remember yesterday we spent a lot of time talking about shrinking core model, and then I think one of the audience asking question, how stable the catalyst. I mean, this catalyst is not stable because the structure keep on shrinking. If you will make it a nitride and then you pull out the nitride, the structure collapse. So in order to model, you have to develop some kind of things called shrinking core model. So that means a constant structure in the change. Anyway, so he basically say something. The conclusion here, I want you to memorize. You need a 1.2 metric ton of manganese, okay, will be needed to produce 100 kg ammonia per day. So my question is, okay, I'm going to write my question. This page I cannot write it. All right, I need to go back. I don't want to leave this page, okay? So I need to write on something. So basically, can you see my handwriting? So he said you 1.2 ton manganese for a capacity of 100 kg ammonia per day. You need this much catalyst. So my question is, his calculations based on all of he described, I don't think it's necessary. What you can estimate is, I'm going back, to produce 100 kg of the ammonia per day, how much catalyst is needed. So here's the data. You already have the data. Hold on. I'm going to leave this on the screen. Okay. So let me do this. I'm going to stop sharing. I'm going to share I'm going to post my question, okay? So remember this example. Here's the question. Okay, so let me write my question. How much manganese? I would say by weight. Is needed for 100 kg per day, 100 kg ammonia per day. Ammonia per day, okay? The plan. So remember this. So keep in mind that the data you are looking for is the per hour or per day and per unit of catalyst, okay? So here's question, okay? And then I want everybody memorize this question. Then I go back to show you the data. How much manganese is needed for 100 kg ammonia per day plant? Okay, this is the question. I'm going back because if you read this paper, it's gonna be very simple. I doubt everyone read this paper. This graph, figure 5. You have all the data from figure 5. Get that piece of data, and then I give it 10 minutes. I want somebody to answer. Okay, you have all the data you need from this figure 5. This can everyone see figure 5? Can you see? Can someone answer me? Can you see figure 5? I'm sharing with you.
Yes, sir.
Okay, all right, so you got data. Okay, so look at figure 5, that's your data. I want to know, based on the laboratory data, and you want to build a 100 kg ammonia plant, and then how much manganese you need?
It is 14,400 kg. 14 metric ton.
I spent 10 minutes, poke around, and then I want some one of representative tell me the answer, and then tell me the how you did the calculation. Okay, 10 minutes. I will see you. I'm gonna be here. Poke around. Let's 10 minutes. So yeah. Yeah, I already show you the example. So yeah.
Is visible to the new site at least. Okay.
Yeah, you have 10 minutes to do this. If someone have answer already, we don't have to wait 10 minutes. You can just tell me, hey, I have answer. I want you to speak very, very slowly how you come up with the calculation, okay?
We need around 14.4 metric ton per manganese per 1,000 kg per day. Sir, can you imagine?
Could you say it again? Have you come up? Just tell me the answer. How much the manganese you need?
14.4 metric tons per day.
Okay, let me write it down. Okay. I'm gonna share. You said 14. How much?
14.4 metric ton. It means 14,400.
14,000
kgs.
kg. Let's round it up. You said 14,000 kg.
Yes, sir.
Okay, very good. Okay, so let's see. 14,000 kg is about 1.4 ton. All right? No, it's 14 ton. 14 ton. All right. So
Yes,
okay. All right. 14,000 kg, about 14 tons. Okay, very good. Okay, so let's see how you did calculation. Okay, so 14,000 kg, and then so then the question, I really like your answer, but this answer may not be correct. So because I want to walk through the video. Okay, so you can still see my sharing. Okay, so all the data are in here, and then remember this guy did all of the description. He say, I'm using shrinking core model. I'm doing all of this. And then he has a 1.2 metric ton of the manganese. Do you see that? So why he said he only need 1.2 ton, and then you need your number is 10 times is his number, all right? So 10 times. So why your number is 10 times his number to produce same capacity? Okay, so it's okay. So let's see let's see how he calculate. You cannot figure out based on his description. You cannot figure out how he calculate because he uses so many things. But I believe the real data is actual here. That's why I'm showing figure 5. Okay, so anybody has different answer? 14 tons. Anybody has different answer? No? Okay. All right. I'm going to show you my calculation. Let's work together. Okay. So read this the caption, figure 5. So this curve is based on the 5 gram of the manganese. All right. Make sense? This curve. So all the laboratory experiment is done using the 5 gram catalyst. And then now we want to calculate how many, now 5 gram of manganese. We want to, and you look at the data. So read this, if you can follow my cursor, let's look at the best data, okay? The best data will be like this. In 50 hours, okay, this is cumulative, 50 hours. And then look at this, the top curve. This is the best performance. What's happening was he used the so-called the sodium hydroxide as a promoter. So every time he used it, and it's getting better. I think let's give this paper some credit, saying, okay, what's your best data? So in 40 hours, he basically reached this data point. So how much is this data point? It's about the 50 hours. It's about 0.0025 mole of ammonia. All right. So I'm going to write it down. So before we come back, so let me see. Keep on. I'm going to repeat it. 5 gram catalyst in 50 hours. The best data point, which is here, he produced 0.0025 mole of ammonia. Do you agree with my reading here? Yes, sir. Okay, is that right? 5 gram catalyst, 50 hours, and then you get this data point. Okay, let's go back to the, because I can only share the one screen with you, okay? So I'm going to stop sharing. Okay, so go back to here. It's very important. It's basically when you scale up, I mean, it tell you how much the the catalyst or the material you need to purchase. Okay, so I would say 5 gram manganese is needed 50 hours. All right. So how much the ammonia produced? 0.0025. All right. So that's why I want to show you the good example. Then we come up with this. So based on this, you should get the number you need. All right. So let's see, 0.025 mole ammonia. All right. So keep in mind 0.0025 mole ammonia, 5 gram manganese, and then 50 hours. Okay. So let's take the data. Let's calculate together. Go back to the copy. Stop sharing. I'm going to show you the Excel. It's easy to. I'm going to share. I'm going to share my Excel. I think I don't think it's a 14. I don't think it's a 14,000. So you should get close enough to 1.2 ton. And then, but I want to let's work together on the calculation. Okay. Here, I want to share my screen. Can you see my Excel sheet?
Yes.
Oh, okay. All right. So this is very important data. 0.0025 mole, 5 gram manganese, 50 hours. I'm converting now. Okay, step by step. So what does it mean? So if first I want to turn this 0.0025 mole into the weight of ammonia. What is the ammonia molecular weight? 17. All right.
Yes.
Makes sense. So 0.0025 mole means all right? So see my formula, 0.0025 more times 17, they become this gram, all right? So now I'm changing this formula now, okay? So I'm changing this into
14 plus 3.
it's 0.0425 gram.
14.
Is that right? So I want to show step by step. I'm only changing one parameter at one time, okay? So I'm changing more into grams. So now it's 0.0425 gram, still 5 gram and 50 hours. Let's keep on changing. Now I'm changing this 5 gram now. So I'm changing this 5 gram 1 gram now. So that means this one need to be divided by 5. So how much? It's I want to make sure you are with me, okay? 0.0085 gram ammonia. Now I'm changing gram manganese. 50 hours, all right? Make sense? I want to come back to specific activity. Does it make sense? So first I change more. And then I divide by 5. Now changing the gram. Okay? So this number divided by 5, change gram. Now I'm going to divide by 50, then become 1 hour. Then picture will be clear now. Okay? So now I'm keep on changing. Okay? So what am I going to do? So basically 50 hours. That means this number divided by 50. All right? 0.085 divided by 50. So what does it mean? The number will be 7 gram Make sense? Okay. So now it comes to specific activity, which is the example I show you. Using the data in the figure 5, you come up with specific activity. This is laboratory data you need. Okay. So what are the curve? I mean, it's meaningful only the shows the the data, the raw data, but you want to calculate this. So now it become clear now. So basically in 1 hour, and then the 1 gram of manganese will produce 0.0017 gram ammonia. So remember I asked you per day, 100. Remember I asked you 100 kg per day and how much needed. Okay, let's keep on doing. So let's change this to per day, okay, times 24, all right? So this number times 24. So what's the number? So it's going to be 0.00408 gram ammonia per gram manganese per day. Are you with me? Make sense? Okay. So what's the deal? So 100 kg, 100 kg means 100,000 grams. All right. So divided by this number, and then you will come up with the weight of manganese. All right. So basically, watch the input line. You should see the formula. 100 kg means 100,000. Okay. Divided by so the result should be how many grams of manganese you need. We will keep on changing. Okay. So the result is very big. Okay. So this is what the result you need. So you need this is basically the gram manganese. So let's change this to the ton. Okay. So from gram to ton. How do you change from gram to ton? 1 to 2, 3, 4, 5, 6. Correct? All right. Do you see my formula? To change this number to ton. So that's the number you need. I think I got even bigger. I thought it was a 2.5 ton. $100,000 kg per day. Anyway, so this is ton. I think something wrong here. I think it should be 2.4 ton. So you have 14 ton, all right? So now the way I calculate is 24 ton. That's even larger.
2450.
Yeah. Somebody can say something. Go ahead.
Got 10,000.
So just before we need, you have given the calculation like for 100 kilo of ammonia, we need around 1,200 kg. That means 1.2 metric ton of catalyst. Okay.
So the paper says 1.2 ton. Your calculation shows 14 tons. I walk you through. I show 24 tons. Yeah. So, but anyway, regardless, I think the key is this is right highlight. You need to come up with per hour specific weight per gram for manganese. How much you need? How the active this is the material. You follow me? So I think something wrong. So hold on. Give me 1 second. I want to check my calculation. Okay.
It should be 24.
Say it again. What you call? What? Can someone getting a microphone? You say should be 24 watt.
It's 24.50 and 10.5 kg. 24. 2450 ton, Dana. 24.5.
So did my calculation match with your calculation?
It is 2450.98 tons, sir.
Okay, cool. So that means that my calculation is correct. So okay, let's go back to the paper. So that's why when I lecture to you, I couldn't figure out how this paper is calculated. No matter how you calculate, I'm gonna stop sharing here. Thank you. I think I'm glad we work together. So if you look at their data, and then there's their data, all right? And then if you read this paragraph, it won't match, because this paragraph says so many things. They even said manganese particle diameter and also the shrinking core model, and then give you a lot of assumptions, but they never show you step-by-step calculation. And then they came up with a number. That's why I sent you the paper for pre-read, and we work together, and then to come up with calculation. So it still doesn't match. So if produce 100 kg ammonia per day, you need 24 ton manganese. That rate is so big. So I think the conclusion will be like this, okay, based on this paper. This is not scalable, because you have so much to produce 100 kg ammonia. The weight of your catalyst is much more than your ammonia produced. All right, how do you handle this? I think that either the data has some problem, or this curve, the unit. I will go back. Either the unit has a problem, or the data has some problem. So, but that's not important. The important thing is when you read the paper, or when you have the laboratory data, you want to scale up. That's the methodology you need to go through. You have to obtain specific activity, means per unit volume, and then per hour, and per day, how much you can produce. Then you scale up linearly. However, this is not this is called a linear scale up, and which is like ballpark would be right. The correct way to scale up, you have to have kinetic data. Kinetic data means you have to read the equation, So it's not linear scale up. Linear scale up is a little bit rough. So there'll be curve kinetically. So you use kinetic to calculate that specific activity, not using laboratory the specific activity. So that means you have laboratory specific activity, you have kinetics, using kinetic curve to predict the specific activity at a larger scale. Okay, so that's the engineering calculation. But for the exercise like today, it's good enough for linear calculation. So anyway, so that's what I'm going to show you, because when I read this paper, I say 1.2 ton, and then per 400 kg, something wrong here. So now when we went through the calculation, we even get a large number. Okay, so do you guys agree with my calculation? We just did together?
Yes, sir.
Okay, all right. Okay, so I think that's very good exercise today. I think we have probably 10 minutes. Let's begin the next lecture, which is the ammonia, the low pressure ammonia absorption, and then after we will continue after you guys lunch break. But I want to get move a little bit further. Okay. All right. So let me go. I'm just sharing this my slide. You guys see my slides, all right? Okay. So we've done the first one. So I planned like 1 hour. I really appreciate. So you guys really looks like someone pre-read the paper, and then when I point to the figure 5, and then they'll give you an example, so you jump in right away. So very good exercise. So, all right. So now I'm talking to the second problem, so-called downstream low pressure ammonia separation. Okay. So someone has a question? Or no question? Okay. So this is Haber-Bosch plan. Okay. In the Haber-Bosch plan, and then the first part here, I'm gonna draw a circle. So you don't have to worry about here. Let's go all about the hydrogen production. So whatever covered, those are hydrogen production. I'm gonna write it down. Okay, it's H2 production. So what you need to worry about or look at it is just this part. That's why in day 1 when they present this Haber-Bosch plan, it's not just ammonia synthesis. It's hydrogen production, which is now is covered. I want you to focus here. But even for the Haber-Bosch plan, your Haber-Bosch reactor is just this little this reactor. Okay, so this is the so this is your Haber-Bosch reactor. After reactor, what you have a condenser, compressor, recycle. All these are high pressure. So why after condenser you have the compressor and recycle? I'm asking a quick question. Okay, here's a question. Ammonia synthesis is 250 bar. So after the reaction, and then there's a gas coming out which contains ammonia, hydrogen, nitrogen, and then they go through condenser, and after condenser, ammonia coming out. See the ammonia coming out here as a liquid, and then hydrogen, nitrogen are recycled. Is that right? Because the hydrogen, nitrogen has to go through the compressor and then recycle. Here's the question. After condenser, why you have to compress the gas in order to recycle? Anybody can answer this question? Why you have to compress? Why don't you just recycle directly? Why you have to compress? You begin with the NH3.
Maybe some reactive hydrogen.
And you begin with NH3, and then you end up with N2 H2 recycled, right?
Yes, sir.
So why? So obviously this recycle loop need to be the compressed, which means you have to build the pressure up. Why? When you see the equation, you should get the answer.
What was the size range of the condenser?
So basically, this is going to be the 250 bar, all right?
Yes, sir.
250 bar gas coming out. Now, when you ammonia has a partial pressure, all right? The ammonia contribute to this 250 bar. Remember, you have three components: ammonia, nitrogen, hydrogen in the reactor. So after this, ammonia, hydrogen before condenser is still 250 bar. Now after condenser, you have to compress it. Why? Because ammonia is gone. Hydrogen, nitrogen will not sustain 250 bars. All right, because the ammonia is gone. All right, the partial pressure. So do you agree? So with ammonia that disappeared, and then this is less than 250 bar because makes sense.
Yes, sir.
So you cannot recycle because the reactor is still at 250 bar. Keep in mind, reactor always 250 bar. You off gas 250 bar now, and then ammonia contribute to this 250 bar. You condense them, then coming out hydrogen, nitrogen is less than 250 bar. Of course, you need to compress them and then make it equal to the inlet here. Okay, so that's why you need a lot of the condenser, condensing, recompression, condensing, recompress. So that's for the Haber-Bosch process. You cannot use this for the low pressure ammonia. Remember, chemical looping or ammonia or plasma will reduce pressure to the ambient. So you don't want to go back to the configuration. Okay, so that's the idea. Now we are going to talk about today how many the low pressure ammonia recovery you have. So okay, all right, I'm going to open up. So this is the basic today. The topic is the plant modeling and the TA. TA stands for techno-economic analysis. Techno-economic analysis is different from accounting economic analysis. Accounting economic analysis, you just analyze the whatever depreciation or the financial data. Techno-economic analysis, you need to have a lot of technical detail because different technical the data will create a different economic outcomes. Follow me? So that's why today I'm going to show you several low pressure ammonia separation, and then that will basically cause the different economic consequence. Make sense?
Yes, sir.
And then this is now I tell the reason why we have to go through the low pressure separation. Okay, so before you guys go to lunch and before I'm talking about the low pressure, I want to compare the Haber-Bosch, the summary. On the left hand side of the column is the Haber-Bosch ammonia synthesis. That's our baseline in the techno-economic analysis, and then this is microwave assisted ammonia process, and then it's a low pressure. It's not ambient pressure, but it's a low pressure. So the comparison is like the Haber-Bosch, a high pressure operation. It's low pressure operation, and then Haber-Bosch, the plant we choose operate 275 bars. Typically, Haber-Bosch plant 250 to 300 bars, but we choose 275 bars in our simulation. So for the microwave, we operate from the ambient pressure to 35 bars. I would say maximum operating time is 35 bars. And then in Haber-Bosch plant, I show you it's condensation separation to obtain ammonia. That's the only method Haber-Bosch can use because it's high pressure. You have to use the high pressure cryogenic condenser. However, for the low pressure, your option will be open. This is real innovation for the low pressure microwave processing because we can choose novel separation, and because we lower the pressure, the recycle and the recondensing are not needed because it's a low pressure operation. You don't have to recompress this gas, or you only need a little bit pressure to recompress it because it's the decrease of the pressure is not that much. And then the store start up and shut down, and the fast start up and shut down. So, and just normally when I give the lecture or the teaching the courses like this, I bring the whole class to my laboratory, having them to see the microwave ammonia synthesis. So pretty much the writer, you flip the power microwave, you see the online the analyzer ammonia come out, because the low pressure operation is easy to pressurize, and also the microwave heating you can heat instantaneously. Okay, you don't have to go to the ramping. But remember I said the Haber-Bosch commercial Haber-Bosch plant take 3 days to start up, 2 days shut down. 3 days start up means you have to slowly pressurize and slowly increase temperature. So once you land up at 500 degrees C and then the 275 bars, that's your condition, 3 days. When you shut it down, you have to basically cool it down slowly. You have to slowly release the pressure. You don't want to all of a sudden release pressure. So it takes 5 days to turn around, but the microwave, we can do it within a minute. So that's the advantage of the microwave. But unfortunately, I'm teaching online, and then you guys you do not have a chance to visit my laboratory. It's a very fast start up and shut down. And also the last the feature, so the most suitable for large scale operation. Ammonia Haber-Bosch plant are built very large. You're talking about 1,000 tons per day capacity. I'm pretty sure ammonia plant built in India using the coal as a feedstock. I think the plant is much bigger. It's probably 2,000 to 5,000 tons per day. Because I used to work in this ammonia field, we actually import the U.S. or around the world import the ammonia from India. India actually is the ammonia or the fertilizer exporter because it's from the low cost feedstock. So enables small scale and modular operation. So typically, if you start a Haber-Bosch plant, you'd have to have enough hydrogen supply, either from coal in the United States and natural gas. So now with the microwave, we use renewable power. We use solar and wind, so that we are dealing with a small scale. Remember the case study? I have you the class calculate 100 megawatt either solar and wind farm. How big the plant you can sustain? It's a 70 ton at the most, compared to 1,000 ton. So basically, the new technology using microwave, you have to have a smaller scale operation. Smaller scale, the ammonia reactor, that means smaller scale downstream separation. So you cannot use high pressure condenser. We're basically using the so-called the novel separation technology, which I'm going to talk about after break. Okay, so it's about the time for the break, the lunch time. I will see you in 1 hour. Okay, is it good? 1 hour?
Yeah. Yes, sir. We'll meet after lunch. Thank you for the
question. After lunch. All right.
Cool.